Welcome to our channel Learn and Learn Engineering. In this video, we are going to discuss about load test on DC compound motor. It's an experimental setup. How to conduct the load test will be discussed in this video. So before getting into this video, we should know about the different types of DC motors. DC motors classified into three different types. One is the shunt motor, series motor and compound motor. So according to the field winding connection, the DC motors are classified. If the series field winding is connected in series with the motor or armature winding, means that is series motor. If the field winding is connected parallel to the armature winding, means that is shunt motor. If we have both the series as well as the parallel winding, means that is called as compound motor. So this is the circuit diagram for a DC compound motor. Here you see the series field winding is also there, the shunt winding is also there. So this kind of connection will be called as the DC compound motor. Okay, in this DC compound motor there are two different types. One is the long shunt and short shunt compound motor. The long shunt compound motor will have a field winding which is connected parallel to both the armature and series field winding. So this is the series field winding, this is the armature winding. So the shunt field winding is connected parallel to both the series field winding and the armature winding. Here the shunt field winding is connected parallel to both the series field winding and armature winding. That's why it is called long shunt compound motor. Here the current equation will be the total current, the load current, or we can consider as the load current, will be equal to the summation of both the shunt field current and the series field current. Here the corresponding armature current will be equal to the series field current. The armature current will be equal to the series field current. Whatever the current flowing through the armature will be equal to the series field. So the number of turns in the series field winding will be less and the thickness of the field winding will be more. So same thing we discuss in the DC series motor itself also. Okay, the corresponding voltage equation has been given. So E, or we can take it as terminal voltage or load voltage, is equal to EB plus IA into RA plus RSC. So this is the corresponding current and voltage equation for long shunt compound motor. So the next type is short shunt compound motor. Here the shunt field winding is connected parallel to the armature winding alone. Here the shunt field winding is connected parallel to the armature winding alone. Here the corresponding total current will be equal to the armature current and ISH, and the total current it will be equal to series field current. Okay, series field winding current. The corresponding voltage equation will be EB plus IARA plus ISCRC. You know that EB is nothing but back EMF. Okay, so these are the two different types of compound motor, long shunt and short shunt. In these categories, according to the field winding connection, we can classify the compound motor into differential compound motor and cumulative compound motor. Characteristics of DC compound motor, we are going to discuss about the torque versus armature current, speed versus armature current, speed versus torque characteristics. So here the first two are the electrical characteristics and the last one is the mechanical characteristics. Let's start with the electrical characteristics. First one is the torque versus armature current. So this is the torque versus armature current characteristics for a DC compound motor. You can see that the difference between the series motor, shunt motor and the differential and cumulative compound motor characteristics have been shown. From this graph you can able to identify that the corresponding cumulative torque characteristics of the cumulative compound motor will lies between the series and the shunt. Okay, so from this graph you have to understand that the torque will keep on increases as the armature current increases. Here current increases, armature current will increases linearly, but in case of differential, okay, in case of differential the torque increment of torque is very less, but the armature current will keep on increases. Okay, so low torque capability is there for differential compound motor, high torque capability is there for cumulative compound motor. But if you see the series motor, for very minimum current it could able to attain the maximum torque. So that series motor is called as high starting torque machine, high torque capability machine. Okay, but the speed is not constant in the series motor. Okay, so differential motor will have a poor torque on full load condition. Next is the speed versus armature current. Here the graph shows the different speed characteristics for shunt, series, cumulative and differential. This line shows the constant speed. Okay, this is the constant speed. Okay, rated speed line. So shunt motor will have a constant speed application so that it lies near to the constant speed, and series motor will keep on reducing as the current increasing. Okay, the speed will not be a constant one, so that we couldn't applicable series motor for a constant application. But in terms of compound motor for a cumulative, it nearly lies beneath the shunt characteristics alone. So we could able to apply for the constant speed application this cumulative compound motor, but the differential compound motor keep on increases, so this should not be applicable for the load condition. Okay, so as the load current increases, the speed increases drastically. Okay, it will damage the machine. Okay, so it is very dangerous high speed, it will run at dangerous high speed. So differential compound motor is not preferable for constant application for high load applications. The next is the mechanical characteristics. There you can see the speed versus torque characteristics. So for cumulative, the speed will maintain as the torque increases, but in differential the torque increases but the speed keep on increasing. Okay, so this cumulative is suitable for application which require high torque and constant speed application. Okay, some of the application of cumulative compound motors. Okay, elevators, rolling mills, punchers, shears, planners, wherever we are using series motor we can use, and also wherever we need constant speed with high starting torque we can use this compound motor. These are some of the application of DC cumulative compound motors. This is the circuit diagram what we are going to do in the lab experiment. Okay, as we know that this is similar to the DC low test and DC shunt motor and series motor circuit diagram. We will have a voltmeter which is used to measure the corresponding voltage, and current ammeter. Here we use 4-point starter, since we having two winding, both the armature winding, field winding, so that in order to create a neutral negative path, okay, earthing point, okay, we have the L2 line 2 connection that will be directly connected to the earth. Okay, negative point. Okay, so this is what the 4-point starter. Okay, and the corresponding shunt field winding, this is RSH, this is RSE, the series field windings are there. So these voltmeter, ammeter ratings are meter ratings are confirmed or calculated according to the nameplate detail of the motor. For a DC compound motor in our lab we have a rated voltage of 220 volt, speed is 1500 rpm, and the rated current, armature current, is nearly 18.6 amps, and the field current will be 1.2 amps nearby. Okay, so if this is the nameplate details of the machine, means then we have to choose a voltmeter more than 220 volt. So I am taking at 0 to 300 volt MC. MC is nothing but moving coil. Here ammeter, rated current is 18.6, so that I am going for 0 to 20 amps. 0 to 20 amps MC. So it's a polarity driven, so we have to carefully mention the polarity. Okay, and the rheostat voltage and current. So here I am going for this rheostat can be calculated from the Ohm's law. V is equal to IR, R is equal to V by I. So we can take it as voltage. V is nothing but 220 volt and the current is nothing but 1.2 amps. So if you put it, you will get nearly 183 okay, 180 ohm. Okay, the current is 1.2 amps. So according to the volt resistance range and the current range, I am going to fix the rheostat value. In our lab we have a rheostat called 220 ohm rheostat with 1.4 amps. So I am going to consider that, or you can consider 175 ohm rheostat with 1.5 amps. Okay, 1.5 amps, anything nearby. We have to consider the current rating. According to the current rating and nearby to the resistance, we have to choose the rheostat value. So same procedure for load test. You have to start the motor, close the switch, and the fuse rating has been fixed 120% of the rated current. So you can fix up to 20 amps or 22 amps. Okay, 120%. So close the DPSC switch, and by using the starter you have to start the motor. Make the motor run at a load, no load, and not on the reading. Okay, apply, or you can from load, applying the load, okay, up to the rated current. Okay, you have to note down the corresponding voltage, current, S1, S2 value, and the speed value. So that the same thing you are going to tabulate in this tabulation. You are going to measure the line voltage, you are going to measure the line current, the corresponding S1, S2 readings will be measured from the weighing machine, and the speed you have to measure by the DACO generator. Okay, other things you will calculate according to the formula, similar to the load test and DC shunt motor concept only. Okay, so you have to take readings up to the rated 120% of the rated current. Okay, you can apply the load directly. Okay, you know how to apply the load. Okay, when you view my video on load test and DC shunt motor, you could able to get that. Okay, kindly go through on it, it will be useful for you. So this is the model graph, performance characteristics and the mechanical characteristics of our DC compound motor. So here this is the speed versus output power. This is the efficiency versus output power, and this is the torque versus output power, and this is the load current versus output power. Okay, so we are going to draw the graph by calculating the parameters according to the tabulation. So from this we could able to identify the performance, efficiency of the machine for different loading condition, different output of what. So for different output power, what about the variation in the speed, for what about the variation in the torque, what about the variation in the frequency, efficiency all can be calculated from this graph. Okay, thank you very much for watching this video. Thank you. We will meet you soon in another video. Thank you.